touch with various, anytime there's a Jan name, I try and check out who it is.
Vahid Petrosyan.
Oh, Vahid Petrosyan, so, he predates me. I mean, Vahid Petrosyan at Stanford, he was much more of a theoretician, and he still is, and he's still, you know, very well known and doing still very good work. And also, one of the professors that I knew when I was at Caltech, Roger Blandford, he's actually gone up to Stanford to, in fact, expand and broaden Stanford's astronomy department. So Vaha is in a much better position now than he ever was. I don't know him very well personally. I know the younger astronomers personally. So there's one who works at the U.S. Naval Observatory. There's one that works at the Very Large Array. That's, if you ever saw the movie Contact with lots of dishes, that's where he works. Let's see. There is one other who actually started off in Los Angeles and went to Cornell. Now he's back at UCLA doing his graduate work there. He works on dark matter. But there aren't that many of us. It's
in Europe? Europe?
I know the names in Europe, but I don't know them personally. And I mean that I see there's papers coming out of Europe that have Armenian names there. But interestingly enough, there's a few that went to Mexico after the fall of the Soviet Union. There are several Armenian astronomers that went to Mexican institutions. And so I saw several of them come to American Astronomical Society conferences. So I haven't heard from them more recently, but somehow they got really good positions at various astronomical institutions in Mexico.
Yes.
Sorry?
You
know, I certainly know Ara very well. Yeah, Ara Chukyan at JPL is, well, he's not an astronomer, I can say that part, but what his main thing though is, his work applies to astronomy, and he does work with astronomers. His work is more with chemistry, and so what he does is he builds instruments to do various kinds of chemical, and so one of the good things is that whenever we see a particular chemical in space and so on, and see, okay, well, what conditions made this happen, so he can do it in his lab. But interestingly enough, the most recent thing that he worked on was talking about chemistry, is that it's basically what's called it's the nose for the space station. So what it does is it takes gases from the space station and analyzes it to get a sense of what the chemistry is going on there. Yes.
What's the process of a star between its explosion and also collapsing into a dwarf? Is that two separate processes, or?
No, they happen simultaneously. It's like when you turn off the pressure at the center of the star, the core starts collapsing. Now, one of two things may happen. Once it hits one of these degeneracies, it may stop. And think about, and basically for that split second when it stops, everything else that was coming down basically bounces off and goes out. But also another thing to think about is as it's collapsing, it's actually creating a lot more energy. Just like when I was saying, you compress a gas, you create a lot of heat. So after a certain point, it's actually generating an enormous amount of pressure. So the outer layers, which are much less held by gravity because they're just further out, basically get blown off. So it's a simultaneous collapse and sort of explosion, but on different scales. Yes?
At JPL, when you guys are deciding which project to push or promote or support, what kind of process do you go through? What determines what you want to do with them? Everybody is for black holes, or some of them are for something else there, or like so whether you can have life here. How does that, like the life versus the black hole teams argue with each other or debate or come with a conclusion?
NASA has sort of made that decision for us. That is, it gives.
But the NASA who decides these things.
Oh, NASA basically, it's the various people. The people who are in sort of the bureaucracy of NASA are the ones who are sort of deciding this. They listen to various scientific committees saying, for example, in astronomy, dark energy, this whole, it's a new concept, very exciting. They're saying, okay, we should start looking into this. Recently, lots of planets around other stars were discovered, exoplanets. That's also a hot topic. Now, it's not the same astronomers doing both, but each astronomer group is sort of pushing, this is interesting, we should be following this. And then they basically make a decision. Now, the way the decision is made, though, isn't just some random bureaucrat making that decision. Within astronomy, it's what's called a decadal survey. There's an entire survey of astronomers that gets done every 10 years. And there's a committee that gets put together. And that committee basically takes the input and starts compiling it to see really where is the community. And once the community decides, saying, really our highest priority is exoplanets and dark energy, let's say. Then they go to NASA and say, this is what the community is saying. And then NASA looks at that and says, okay, we're now going to have missions that study exoplanets and dark energy. And then JPL says, ooh, NASA's looking for exoplanet and dark energy. Which of our scientists are working on? How would we best test this in terms of a space mission? And then so you put a team together and people start sort of brainstorming. And then you have this thing called Team X. Team X is basically, you get a lot of engineers together, you get the scientists together, and everybody says, the astronomer says, I want a 5-meter telescope. And the engineer says, great, that's $2 billion. Your budget is $500 million. Oh, how big of a mirror can I have? Half a meter, 1 meter. Okay, 1 meter mirror it is. What science can I do with 1 meter for what I'm trying to do? Nothing. Okay, let's start over again. So you go back and forth and back and forth. It's like, well, you can make your mirror bigger if you sort of give up on this, and you can do this, and so then it's all this back and forth until they say, okay, we can have a 1.2 meter mirror which does this kind of observations, which will give us the answer for dark matter, dark energy, or exoplanets, because that's what we're looking for. So and then NASA puts out a call. I want an exoplanet mission. And so the JPL people say, here's an exoplanet mission for your budget. And so it's community driven effectively, but that's done about every 10 years. And this decadal survey for this coming decade, in fact, will be, everybody is expecting the committee to report by September, we hope. The papers all went in last year. They had town halls. I was at them. People asking, what do you think is important? Where are we going? What are the questions you think are the most important? How is the community dealing with all of this? So it's a very sort of broad sort of effort in trying to get what's the most exciting, the most cutting edge, and at the end of the day, though, it's that versus your budget. So we'll see where we go from here.
How many reports did you get?
Sorry?
How many reports are there?
I don't think they've actually given a total number. I do know just hundreds. There are definitely hundreds of reports. I know, and on everything, on whether, not just space missions, on all aspects of astronomy. The Hubble survey should comment on, how graduate students are being treated, because it's good or bad, or you should do it this way. So.
The ground-based telescopes are usually in Hawaii and Chile.
Yes.
There's an advantage to that. Does the Armenian Mountains have any advantage to compete with those locations?
No, the Armenian Mountains are probably the worst situation you can be in. Partly because the reason why you put them in Chile or in Hawaii, or in fact California, this is where permanent mountaintop observatories started. Lick Observatory in San Jose was the first permanent mountaintop observatory. It worked so well, and that was in 1888. It worked so well, they put the Mount Wilson Observatory here above Pasadena, and that worked for many years, and then there's Palomar. Why? The airflow coming off the ocean, the cool air that comes from the ocean, as it goes over the mountains, it actually provides a very stable air above the telescopes. Same with, obviously when you're an island in the middle of the Pacific, you have the same thing as well. Chile, it's the same thing actually, but they're at a much higher altitude, so you have no actual moisture above you. So the less moisture you have, the better. It means you don't get rained on, you don't get clouded out. So those are the positions. People, there's lots of snow on Aragats, and they're not even that high. Armenia is not very well positioned for that. And even Byurakan itself, it's next to the village of Byurakan. No modern telescope is actually next to any kind of a living area. You want to get the people, the smoke from the cars or the heat from your air conditioners and heaters and so on, away from your telescopes. You want as little disturbance as possible. So at the time when they put it there, it was good. There's a lot of observatories where at the time it was the best that they could do. And Armenia has only the mountains that it has, so might as well do it. You then pick the science that you're going to do. You don't compete with the 10 meters on Hawaii or the 30 meter in Hawaii that will come eventually that they're talking about. there's stuff that you can do that's not based on just simply collecting more light. The idea is that you can do